So now let's take a look at some methods that have been used in the past about age dating the Earth. These are all methods that have been employed, however, did not give us the correct answer. And then by the time we get to the end here, we're going to see how we actually do it. So like I said, we're going to get into a little bit of baby chemistry. So some of the early ideas about age dating the Earth, the first one came from Archbishop James Ussher, who in 1654 figured out the genealogy in the Bible, the begats, right, whomever begat whomever and whomever. He determined by backtracing that the Earth was created, this is my favorite, on October 23rd, 4004 BC at 9 a.m. I truly love how specific that is. I think that's fantastic. So the idea was that the Earth was about 6,000 years old. We definitely know today that that is not true. Right? And you're going to see how we get the age dates for the Earth to know how old the Earth is. Plus, it's a lot of evolution and a lot of things going on in the Earth to jam into 6,000 years. However, that was the first idea about age dating the Earth. Now, you see, this idea led to catastrophism, right, which we saw in the last chapter, right, with Cuvier and Brongniart. But it wasn't until over 100 years later that the next idea came about for the age of the Earth. Which shouldn't surprise you, because who wants to go against the Catholic Church in the 1600s? Nobody, right? So 100 years later, James Hutton, who you may remember from the last lecture as well, came up with kind of a general idea. He went and visited Hadrian's Wall, which is a picture right here. It was built by the Romans in Britain to separate the Romans from the rest of the world, kind of like a wall of China. And this wall was built in 122 AD, so it's old. So by the time Hutton looked at it, it was about 1,600 years old. And he noticed, and this picture's from today, so you can imagine it looked a little bit better in the 1700s, he noticed that very little had changed with this wall. So he thought, right, if the Earth is only 6,000 years old, should this wall look that good? Right? The answer is no. Right? When you take into account all of the things that would have had to have happened in those 6,000 years. So, he was the first person to really say that the Earth has to be older than 6,000 years. He didn't even venture a guess. He just said, okay, the Earth is definitely older than 6,000 years. How old? I don't know, but it's definitely a lot older. Then, over 100 years later, Lord Kelvin started doing some calculations. Those of you that have had astronomy or physics may recognize that as the Kelvin from the temperature system. He recognized, right, that the Earth once started out as a molten ball. And he wanted to figure out if the Earth is this given size, right, this volume, mass, and density, how long would it take for the molten ball to cool down for it to be solid? And he figured out that the Earth had to be about 24 to 40 million years old. Now, the problem with this is the Earth molten, right, all the way through? Now, the answer is no, right? We know, or solid, all the way through. The answer is no. And we know that there are some layers inside of the Earth, right, such as some of the lower parts of the mantle and the outer core, that are liquid. They are not solid. So there's definitely a problem, right, with Lord Kelvin's calculations. The next person to try to age date the Earth was John Jolly, which I think is the best Irish name I've ever heard. He recognized, and this is something we're going to talk about when we get to chapter 9, that the ocean once started out as fresh water. Like I said, I'm going to address that when we get to chapter 9. He recognized that salt dissolves easily in water. Salt forms from evaporation. All water has salt in it, whether it's fresh water or salt water. It's just in very low concentrations in fresh water. You've probably noticed this. If you've ever left a pot of water on your stove and let it boil, and maybe you've accidentally let it boil all the way so the water's evaporated, you'll notice that there's a white ring, okay, inside that pot. That's salt. And that's how salt forms, from evaporation. So think about California, right, where all of these lake beds are drying up. Well, it's leaving salt behind. Eventually, what would happen is a river would come back through that salt layer, and it would dissolve that salt layer, And that salt would work its way out into the ocean, and over time make the ocean saltier. So John Jolly recognized this. So he figured out, right, if I have this much water, how long would it take to get to this salinity that it is today? And he figured out that the Earth was about 90 to 100 million years old, which again, we're reaching back further in time, so that's good. However, he couldn't account for recycled salt, right? Salt can come into the ocean and it can go out of the ocean, right, in different minerals and salt deposits. So he had no way to account for that. The next idea was by taking a look at the thickness of sedimentary rock, namely here in the Grand Canyon. Right, so if you look at the Grand Canyon, right, you say, okay, well, we've got this much rock. How long would it take to deposit this much material? And in 1860, they figured out to be about 3 million years, and in 1910, they went back and recalculated it and said, oh, it probably took about 1.6 billion years to deposit all that material. Now, again, that's great. We're reaching back further in time. However, there's problems here. Material doesn't deposit at a steady rate all the time. If you think about it, right, when is the Mississippi River the highest? Well, in the springtime, right, as all the snow from up north starts to melt. As that higher influx of water comes in, it's bringing more sediment. So you get higher rates of deposition, right, in the spring and lower rates in the winter. So these rates are not equal. Right? So we can't really figure that out. Plus, right, we talked about unconformities in the last chapter. Right? You can even see there's an unconformity right here. So there was no way to account for that. Now, the last way was by Charles Lyell, which you may remember him from the last chapter as well. Now, Charles Lyell loved to collect snails. He was a snail guy. And he collected all of these snails and laid out these shells. And he laid them out from the most simple to the most complex and said, all right, how long would it take for this simple shell to evolve to this complicated shell? And he thought the Cenozoic took about 80 million years, which he actually overshot it. We know the Cenozoic today is only the last 66 million years. So, how do we actually get the age? Well, this was discovered in the late 1800s by Henri Becquerel, and this was looking at radioactivity. I was very excited. I actually got to go into his lab when I went to Paris about 5 years ago, so that was pretty exciting. But what Henri recognized is that we have some minerals that are unstable. Because they're unstable, they're going to start giving off particles. And those particles are given off at a regular rate, like a pulse. So once you count those particles like a pulse, you can figure out how old that rock is. So in this next little bit, we're going to talk about how we actually do that. So we're going to get into baby chemistry.